This is a video on hypothesis testing for a mean when the population standard deviation, sigma, is known. So we'll work through an example. This process can be used when the standard deviation for the population is known. When the standard deviation of the population is not known, which is actually more common, we'll use the t distribution. So this is a separate process that we'll describe in a separate video. All right, so here's our example. Scores on ACTs, that's a college entrance exam, are normally distributed with a mean of 20.8 and a standard deviation of 5.8. And when we said, this is something we can use when the population standard deviation is known, that's what we're talking about here. So this is the mean for all ACTs in a given year and the standard deviation of all ACTs in a given year. So this is a population standard deviation and we know what it is. So this is the process we can use in that case. An online prep course helps students study for the ACT and to study whether the prep course improves ACT scores, 60 high school seniors are randomly selected to participate in a prep course. They'll use an alpha equals 0.05 level of significance to test this claim that the online prep course improves students' scores. The 60 students take the prep course, and after the course, their average score on the ACT is 22.1. So the first question is one I think you can do already. It's just, is this a one-tailed test or a two-tailed test? And write the null and alternative hypothesis. So we haven't done any examples like this with part 2 and 3 yet. But right now, pause and try part 1. So pause, try part 1, and then we'll look at it together. Okay, so is this a one-tailed test or a two-tailed test? This is a one-tailed test because it specifically asks whether the prep course improves test scores, not changes them in either direction. So we're not looking, is the mean larger or smaller? We're just asking, is the mean for this group of students or for people who take this prep course, is the mean larger than the population mean was to begin with? We see that for the sample it is larger, but we're asking, is this statistically significant? Is this enough evidence to show that it will typically be larger or on average it's larger? And again, we can tell it's a one-tailed test because we're asking whether the prep course improves ACT scores. So that improves is the piece that tells us that it's a one-tailed test as opposed to just different in one direction or the other. So it's a one-tailed test, and our null hypothesis, H0, is that the mean for people who take this prep course is still the same as that of the general population, is still 20.8. Our alternative hypothesis, because it's a one-tailed test, does the prep course improve ACT scores? Our alternative hypothesis is that the mean is greater than 20.8 for this group. Okay, so now let's talk about the process for part 2 for finding the p-value, the probability of a result at least this extreme, assuming that the null hypothesis is true. So to find the p-value, we're actually going to use the same process we did before in this course, where we found probabilities for sample means using the central limit theorem. That's where we did a z-score, and our z-score was the mean of the sample minus the mean of the population divided by the standard deviation of the population. And the mean of the sample is that 22.1, the sample of those 60 students. And when we're talking about the overall mean of sample means of size n, here size 60, we're assuming the null hypothesis that the true population mean is still 20.8, even for those with this prep course. And sigma x bar, that's the standard deviation for sample means of size n. So for that, we don't just use the given standard deviation in the problem. We use the given standard deviation divided by the square root of the sample size. Because as the sample size increases, the amount that those sample means will deviate from the population mean will shrink. It will become closer and closer and closer together. So this gets smaller as n, the sample size, gets larger. And yes, so we're still going to find the z-score, and that's the sample mean minus the mean for the population over the standard deviation for the sample means. Since this is something we've done before, I'd like you to try to pause and try to find the z-score for this problem. Here are the details again, with all the details of the problem here. So do pause for a moment, try this out, and then I'll work through it in just a second. Okay, we have our mu sub x bar. The mean of the sample means is the same as the original mean according to the null hypothesis, 20.8. Sigma sub x bar is this old standard deviation divided by the square root of the sample size, so 5.8 over square root of 60, which gives us 0.749. And so our z-score, the number of standard deviations that we are above or below the mean, is x bar minus mu sub x bar over sigma sub x bar. That's 22.1 was the sample mean for these 60 students, minus 20.8 divided by 0.749. And we get a z-score of 1.74, or 1.735 if we round differently. So we want to now use a normal table or computational device to find the probability of a z-score being greater than or equal to 1.74. So once again, I would like you to pause and try this step before I go on with it. I'd like you to use a standard normal table or a z-score chart to find the probability of a z-score being greater than or equal to 1.74, and that is the p-value for this problem. So pause and try this out. Okay, we're now going to use this standard normal table or z-score chart to find the p-value. So we're looking at the positive z-score side, since this is a positive z-score, 1.74 standard deviations, almost 2 standard deviations above the mean. And remember, with this z-score chart, the column gives the first up to the first decimal point, and the row gives that, and the column gives the second decimal point. So 1.704, that's 1.74, and we get a probability of 0.9591. But remember that the z-score chart always gives the area under the curve less than or equal to that z-score. So the value, that 0.9591, that's referring to the probability of being below 1.74. What we're looking for with the p-value is the probability of being at least as extreme as 1.74. So we're looking for the probability in the tail, not in the body. And that probability in the tail, since the total probability under the curve is 1, that means this red probability, the probability we want in the tail, is 1 minus this probability here. So because we're looking at the probability of the sample mean being greater than or equal to it, that's the probability of z being greater than or equal to 1.74. Anytime we have greater than with the table, we have to do 1 minus that value to find the smaller value in the tail. So 0.0409 is our p-value. And we're going to talk about what that means next. But again, one more time, I'd like you to pause and think before I go forward. So what should the study conclude? Explain your answer in context. So pause and think about this. You should compare the p-value with the level of significance for the test. So take a look again at the wording of the problem. Think about this, pause, and we'll talk about it in just a moment. Okay. So the p-value is 0.049. This means that assuming the null hypothesis, that's assuming the prep course does not change the average ACT score. In other words, with the prep course, the average ACT score is still 20.8. It's still possible that even if the average score is still 20.8, it's still possible that a group of 60 students could have an average different than that, could have an average of 22.1 or higher. What is the probability of that? The probability of that is 0.0409. The probability of 60 random students having an average score of 22.1 or higher, assuming the general average is 20.8, is 0.0409, assuming the prep course does nothing. So our p-value, 0.0409, is less than alpha, the level of significance. So alpha, the level of significance, was 0.05. That's larger than the probability we got. Because the p-value is smaller than the level of significance, that means that this is relatively unlikely. It happens less than 5% of the time. And because 0.05 was our cutoff, and we said if the results of the experiment are less likely than 5%, less likely than 0.05, we will say that that's enough evidence to reject the null hypothesis. Remember, the null hypothesis was that the mean is that scores on ACTs are unchanged by this prep course. The alternative hypothesis was that the prep course improves the scores. So we are rejecting the null hypothesis. We're saying this is enough evidence to say that the prep course really does improve scores on the ACT. And so in context, this experiment gives us enough evidence to say that the prep course does improve ACT scores at an alpha equals 0.05 level of significance, and the p-value is 0.049. So just as a very brief recap, the process to find the p-value when hypothesis testing for a mean where sigma, the population standard deviation, is known, is to first find the z-score for the sample mean, and it's the sample mean from the experiment minus the mean assumed by the null hypothesis divided by the standard deviation of the sample means, which is the original standard deviation for the population, over the square root of the sample size. And then once you have your z-score, you then use the normal distribution to find the p-value.